Hello and welcome to this video for the Forces and Motion module for the OCR A-Level Physics specification in the Work, Energy and Power submodule, looking at the topic of power and efficiency. So if we've been successful and we've learned in this lesson, we should be able to define the concept of power and the unit of the watt, define and understand the importance of mechanical efficiency, and calculate values using the concepts of power and efficiency. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. We're going to be looking at 3.3.3 power, including power, the unit of the watt, P equals W over T, P equals FV, the efficiency of a mechanical system, and efficiency is equal to useful output energy over total input energy times by 100. Now, in any energy transfer process, the more energy transferred, the greater the power of the transfer process. This is because that the energy transferred, or the work done per second, is the power. So power is the rate of energy transfer, or the rate of work done. Now we can work out power with the following equation. Power is equal to work done in joules divided by the time taken in seconds. Now the SI unit of power is the watt. Now we define 1 watt as 1 joule of energy transferred, or work being done, in 1 second. So we can write 1 watt is equal to 1 joule per second. Now as we know that 1 joule is equal to 1 kilogram meters squared per second squared, this therefore means that 1 watt is 1 kilogram meters squared seconds to the minus 3. Now there are situations where a constant force must be exerted on an object to maintain its constant speed. Now an example of this is a car travelling flat along a road at a constant speed. Now in this situation, the resultant force on the object will be 0. Now the rate of work done by the forward force provided by the engine therefore must equal the rate of work done against the frictional forces acting on the car. So we can say that the work done by the engine is transferred into the internal energy of the surroundings by resistive forces. Now as a constant force F moves the car a distance x in time t, we can say that the work done by the force W is equal to the force times by the displacement, or in this instance F times by x. Now we have just said that power is equal to work done over time. Now we know the work done is Fx, so therefore the power is Fx over time. Now we know that velocity is equal to x over t, the displacement over the time. So we can sub that into the equation to say that power is equal to the force times by the velocity of the object. Now you can use this particular equation in a variety of situations where a constant force is necessary to maintain a constant speed. Now examples include a swimmer travelling through water at a constant speed and a skydiver falling through the air at terminal velocity. So not only is power in watts equal to work done in joules over the time taken in seconds, but power in watts is also equal to the force exerted in newtons times by the velocity in meters per second. Now remember that the force exerted must be in the direction of the motion, so we may need the horizontal or vertical component of the force. Now when a powered object moves at a constant velocity at a constant height, the resistive forces are therefore equal and opposite to the motive forces. So like we said before, we can say that the work done by the engine is transferred into the internal energy of the surroundings. Now this equation of P equals Fv is used when an object is undergoing constant velocity. So therefore the force exerted calculated could either be the motive force or the resistive forces, as they are equal in magnitude to each other. Now when a powered object gains speed, therefore the output force exceeds the resistive forces acting on it. Now, this therefore means that the work done by its engine increases the kinetic energy of the object and enables it to overcome the resistive forces acting on it. So let's have a look at a few examples of this. So consider the following. We're using a crane, and the crane lifts a load of 1,500 kilograms at a height of 25 meters at a steady rate in a time of 2 minutes. What is the power of the crane? Well, we know the work done is the energy transferred, which is mg delta h, because we're looking at potential energy. So therefore it's 1500 times by 9.81 times by 25. So therefore it is 367,875 joules. We can then use this to work out the power of the crane by doing power is equal to work done over time. So there's 367,875 over 120 minutes into seconds. So therefore it's 3066 watts. The next example looks at the following. What is the resistive force on a cyclist who has a leg muscles of power 200 watts each and who reaches a top speed of 10 meters per second on a level road while cycling? So we know that P equals FV. So in this case, we can work out that F is equal to the power over the velocity. So it's 200 times by 2, as the cyclist has 2 legs, as shown in the image, divided by 10, so therefore our force is 40 newtons. Now, the principle of conservation of energy states that energy cannot be created or destroyed, but energy can be transferred from one form to another form, but the total amount of energy in a closed system will not change. However, this doesn't mean that processes and machines convert all their energy into useful work. In particular, thermal losses can mean that some of the input energy is not converted into useful output energy. No device, with the possible exception of a heater, transfers all inputted energy into useful energy. Now, when it is stated that energy is lost, it means that the energy has been transferred into a form that cannot be used or transferred into a form that can easily be used. Now, often work done against friction will cause thermal energy to be produced in the energy transferred. Now, a measure of how much input energy is transferred usefully by a mechanical system is called efficiency. The more useful energy gained out of a machine for what you put in, the more efficient the machine is. So the greater the efficiency, the greater the percentage of input energy converted. So we can say that efficiency is equal to the useful output energy over the total input energy times by 100, or conversely, efficiency is equal to the useful output power over the total input power times by 100. Please note there are no units for efficiency, and efficiency can be expressed in terms of a decimal or a percentage. Now, due to the conservation of energy, efficiency can never be higher than 100% or 1.0. Now, the efficiency of machines or processes can be improved in most cases by insulating an object from heat loss. So let's look at an example calculation. Consider the following. A meat grinder has a useful energy output of 725 joules when making mincemeat. If its efficiency is 89.1%, work out the total input energy. So we know that if efficiency is equal to the useful output energy divided by the total input energy, well, therefore the input energy is equal to the useful output energy over efficiency. So it's 725 over 0.891. We've converted our percentage into a decimal. So therefore it equals 814 joules. So to summarize what we've learned in today's lesson, we've looked at the concept of power, the unit of the watt. Power is equal to work done over time taken. Power is equal to force times by constant velocity. The efficiency of a mechanical system, and efficiency is equal to the useful output energy over the total input energy times by 100. So if we've been successful and we've learnt in today's lesson, you should be able to define the concept of power and the unit of the watt. Define and understand the importance of mechanical efficiency, and calculate values using the concepts of power and efficiency. So thank you very much for watching this lesson on power and efficiency, which is part of the work, energy and power topic in Module 3, Forces of Motion. Thank you very much and have a lovely day.